In this written problem, we have two objects, the block and the box. The box is being moved up the incline, which causes the block to move to the right. There is friction on the horizontal surface, but there is no friction on this ramp. The first thing we need to do is to draw a free body diagram for each of our objects, specifically the moving box and then the block. Doing so, we start by drawing a dot to represent the object, and start with the block first. And as always, there's going to be a force of gravity on it. There's a normal force perpendicular to the surface. There's a tension force from the rope. And because it's moving and the surface has friction, there will be a friction force pointing to the left. For the box, we again draw a dot for it and have the force of gravity acting on it. We'll specify box and block for each of these. There's the tension force acting on it from the rope, a normal force on it from the surface, and the applied force that's pulling it upwards. And that's it. For part B, we now have to write Newton's second law for our free body diagrams that we just drew above. For the block, parallel to the incline means we want to look at these two forces, or not the incline, the horizontal surface, whichever. Anyway, for our parallel or x direction in this case, we have a force pointing to the right as the tension force pointing left is our force due to friction, and because the whole system is moving with an acceleration of 0, we have our right-hand side ma equal to 0. That's not enough because we also need to rewrite our friction force in terms of the variables requested. And so, going one step further, we can write this as tension minus mu k times the normal force, which in this case is labeled as N1. In the perpendicular or vertical direction, we have a normal force minus the force due to gravity, and because the block is not moving up or down, this is also going to be equal to 0. For the box, it will help us if we use a tilted coordinate system, where parallel, or x, is going to be parallel to the incline, and perpendicular, or y, is going to be perpendicular to the incline. Doing this, we can then decompose our force due to gravity into components, where this angle is going to be theta, this side is going to be mg cosine of theta, and this side will be mg sine theta. With that, we can now go ahead and write Newton's second law in the x and y directions. So for the x, or parallel direction, we have all of the forces pointing up the incline, which is just the applied force F, minus all the forces pointing down the incline, which is the tension force and that component of gravity. And again, because everything's moving with constant acceleration, our right-hand side is equal to 0. Not constant acceleration, constant velocity, which means a is 0. For the perpendicular direction, we have our up force, N2, minus our down force, which is the component of gravity. And again, that's equal to 0. Moving on, we now need to solve some computational problems, so it will help us to go back to the top and figure out what are all of our numbers. The box has a mass of 1.2. The angle is 30 degrees. The block has a mass of 3. And the coefficient of kinetic friction is 0.5. And the system moves up the incline a distance of 0.4. So the first computational problem wants us to solve for the tension force when the block is moving to the right, the box is moving up the ramp, and again, everything's still going at constant speed. So we can use our equations that we wrote in part B to solve this. So we want to find our tension force. We could use this equation here for it. So I'd have that tension is equal to mu k times my normal force on the block. Block, right? Yes, block. And then I could use this equation to solve for N1. So if N1 minus mg is equal to 0, N1 is equal to m1g, and so my tension force will be mu k m1g, and plugging in numbers we have 0.50 times 3 kilograms times 9.81, which ends up giving a value of 14.7 newtons. Next asked to find the change in gravitational potential energy of the block as it moves right and the box as it moves up the ramp. And we're assuming the block never reaches the pulley, so the box is the only one moving. And so what we'll want to do is again draw a triangle here, where we're told that our box moves some distance 0.40 meters up our hill. The hill has an angle of 30 degrees, and ultimately I'm going to want to know that h value because the change in gravitational potential energy is just going to be equal to m2 gh, because the box is the only one that moves actually above the ground. How much does it move above the ground? Well, based on this triangle, I can solve for h using sines and cosines. H is the opposite side, so I'll use sine, and that's going to be equal to d sine theta. Plugging that in over here, and substituting in the numbers. This gives us a change in gravitational potential energy of 2.35 joules. For the final problem, we're asked what is the work done by the applied force as the box moves up the ramp that distance d at a constant speed. And this is similar to the last multiple choice question on this exam. Assuming the box moves at a constant speed, our change in kinetic energy is going to be 0. And so we just need to figure out the net work done on the box. Redrawing my free body diagram for my box, again, just for reference, I have gravity, the applied force, the tension force, and the normal force here. Only the applied force, the tension force, and the force due to gravity do non-zero work. And now I can solve for the work done by the applied force by calculating the work done by tension and the work done by gravity. For my tension work, this is going to be my force of tension times the displacement d times cosine of the angle between those two vectors, My object is moving up the hill. Tension is pointing down the hill, so the angle between those is going to be 180 degrees. And for the work done by gravity, that's going to be equal to the negative change in the gravitational potential energy, which we actually just calculated in the previous part. Continuing on, cosine 180 is a negative. I have tension times d minus delta U grav. Solving for the work done by the applied force is going to give me the tension times displacement plus delta U grav. And at this point, I can use the value I got in part C for tension, 14.7, times D, which is 0.4, plus the change in gravitational potential energy, which I calculated in the previous part. Doing all of this gives me a final work done by the applied force of 8.23 joules.